So we're really just going to take the time here to look at the core version of the common gate amplifier. I'll explain why we don't need to worry about a gate resistance or emitter resistance and all of that kind of stuff here in just a moment. So if we look at our common gate core, we have the following circuit. So here's our supply voltage VDD. Then we have some drain resistance RD. Our output voltage will be taken here at the drain. Our input voltage would be applied here at the source. And then we have some DC voltage applied here, resulting in a small signal model as follows. So here's our gate terminal. We have an open circuit between the gate and the source. So here's our voltage VGS. Here's our source terminal where our input voltage is applied. GM VGS goes here. R naught is here. Here's our drain resistance RD. And here's where we're measuring our output voltage, right? So finding the voltage gain of this circuit isn't particularly difficult. It's going to follow almost exactly the same steps that we had earlier, but things are actually going to be a touch easier because we don't have an R pi to even remotely worry about, right? So much like we saw in the common base amplifier, we can see that Vn is just negative VGS in this case. So let me write this out. So we know that Vn is equal to negative VGS, applying KCL at our drain node. We are going to have negative GMVN. So that's our GM-VGS contribution. But then we're going to have V out minus VN over R naught. And lastly, we are going to have V out over RD. Set this equal to 0. Once again, all of our VN terms have a negative sign, so when we move them over, they're all going to become positive. This is very easy to split up. And so what we'll have is Vn times 1 over R naught plus GM is equal to V out times 1 over R naught plus 1 over RD. And therefore, our voltage gain looks like R naught in parallel with RD divided by R naught in parallel with 1 over GM. So this is our formal voltage gain relationship, but recognizing that 1 over GM is much smaller than R naught, this comes out to be approximately GM times R naught in parallel with RD for 1 over GM much smaller than R naught. The voltage gain relationship's incredibly similar, no reliance on beta or anything like that. So this part was fairly straightforward and easy. To determine our input resistance, we're going to look at that small signal model yet again. We're going to wind up applying KCL at both our source node and our drain node. So let me just make a copy of this guy right here. So the only real change that I'm going to make to my small signal model is I'm no longer going to call this voltage V out. I'm just going to call it a nodal voltage VD like so. And I'm going to change V in to V test. And now I'm really just solving for the quantity I test, right? So once again, we can see that V test is negative VGS. Applying KCL at the drain is effectively just going to give us our voltage gain relationship that we just came up with. So that's going to be VD is equal to, let's scroll up here for it, R naught in parallel with RD. Divided by R naught in parallel with 1 over GM. And I'm going to expand this out a little bit. So to me, I know that R naught in parallel with RD is going to look like a fraction because it's going to have R naught times RD over R naught plus RD. I know that R naught in parallel with 1 over GM is also going to look like a fraction. And since I'm dividing fractions, I can just take my fraction in the numerator and multiply it by the reciprocal of the fraction in the denominator to get everything stretched out, so to speak. So that's going to look like R naught times RD divided by R naught plus RD. And then over here, I'm going to have R naught times 1 over GM, and then an R naught plus 1 over GM. I can see very easily that this R naught cancels this R naught. The last thing that I'm going to do is multiply by GM over GM so that I don't get fractions where I don't want them. So that is going to effectively cancel that guy right there. And what I'm left with is GM R naught plus 1 times RD over R naught plus RD. So this is just another way to, times VN, or V test in this case, sorry. This is just another relationship that we can use for the voltage gain. Whoever just accidentally unmuted themselves, please remember to remute yourself because the echo bothers you. So here is what happens when we do KCL at the drain. Now we're going to do KCL at our source. So the current flowing into our source is going to be GM VGS and VD minus V test over R naught. The current flowing, the way that I have I test written, that's also flowing in. So let's write this out. So we have I test flowing in, and then we have a GM VGS, which is going to look like negative GM V test. And then we also have a VD minus V test over R naught. Set this equal to 0. Rearranging things, we can say that I test is equal to positive GM times V test plus V test over R naught minus VD over R naught. Are we all okay with that? So that looks like V test times 1 over R naught plus GM minus 1 over R naught. And now I'm simply substituting in my relationship for VD in terms of V test from up here. That's going to look like GM R naught plus 1 times RD divided by R naught times R naught plus RD. Actually, sorry, I have an extra R naught in there. I'm counted it twice. Times V test. There we go. Make sure I did that substitution correctly. Everything looks groovy there. So factoring out the V test, I wind up having GM R naught plus 1 divided by R naught. So let me explain where this guy right here came from. I'm just multiplying this guy right here by R naught over R naught so that I can lump those together with a common denominator of R naught. So GM times R naught plus 1 divided by a common denominator of R naught there. Then what I'm going to do is I'm going to multiply this bit by R naught plus RD over R naught plus RD so that I have a common denominator for the whole thing that I can lump together. Like so. And then I'm going to wind up subtracting GM R naught plus 1 times RD. Like so. So just to be clear here, because I did a lot of stuff in this one step, I'm really just trying to combine these two ratios together with a common denominator, right? So I can see on this side right here that my denominator would look like R naught times R naught plus RD. So in order to fix things, I effectively said, let me multiply this GM right here by R naught over R naught, giving me this relationship. Then I multiplied by a factor of R naught plus RD over R naught plus RD to give me a common denominator of R naught times R naught plus RD for the whole damn thing. And now it should be very, very easy to see that the GM R naught plus one times RD gets canceled out by the GM R naught plus one RD over here, leaving me with just a GM R naught plus one times R naught in the numerator. The R naughts are going to cancel each other out, so that we have V test times GM R naught plus one over R naught plus RD. And from here, our input resistance is V test over I test, which is just going to be the reciprocal of that relationship. So R naught plus RD divided by GM R naught plus one. So I'm being honest, this is the only part that's really substantially different than what we saw with our BJT representation. And it's really not that different. It just, we had betas and all that kind of good stuff in there that I needed to get rid of. Okay. For our output resistance, which had no dependence on R pi whatsoever, we should get the exact same result that we had previously, which was, so let me just put this down here. So if we look at this circuit where our source is now grounded, and we're applying a test voltage source, what can we see as our output resistance? Yeah, R naught in parallel with RD. So hopefully, very obviously, since the gate is at ground and the source is at ground, VGS is obviously zero, which means that looks like an open circuit. So all we see is these two resistors in parallel. All right, so let's talk our way through what would happen if we had a resistance connected to the gate. So if I had a resistance here, call this RG, would that change our voltage gain relationship at all? Not even a little bit. If I put a resistance here, RG, would that change my input relationship, input resistance relationship? Not even a little bit. Will it change my output resistance? Not even a little bit. Okay. What will the effects of emitter degeneration be? Or excuse me, source degeneration in this case? Whatever we found for Rn will just be in parallel with Rs. All right, so we're done with the common gate amplifier. We know how it works in every conceivable configuration that we could throw at it. Okay, so the last circuit that I want us to analyze is the common collector, also known as the emitter follower amplifier. Okay. So our fully biased amplifier is going to look something like this. So here is our supply voltage, VCC. Here's our resistor R1. Here is our resistor R2. The collector terminal of the transistor is actually connected directly to our supply voltage in this case. So there is no RC for us to speak of. Here is our resistance RE. For the input side of things, we're going to apply our input signal to the base terminal. And we're now going to measure our output at the emitter terminal. So this is what our fully biased device is going to look like. And once again, we're going to break things down into smaller things to see how everything shakes out. So let's look at our common collector core. So that's going to look something like this. Here's VCC. Here's VN. Here's V out. And here's RE. So our small signal model should look something like this. Our collector terminal is grounded. And then down here, actually, let me move this guy over. Nope, sorry, thinking about it backwards. Here's RE. And this is our voltage layout. So I personally think that there's a simplification that we can make here that'll make things a touch easier. Anybody see what that simplification might be? And could do that, but R naught is connected between the emitter terminal and ground. RE is connected between the emitter terminal and ground. So realistically, we could just lump these two resistors together from the jump and make our life easier, right? So we could just call this guy right here R naught in parallel with RE. And that's the circuit that we're analyzing. So if we're trying to find our voltage gain, this is actually going to make things Not particularly difficult, right? So we're going to apply Kirchhoff's current law at our emitter node. So let me see. So finding our voltage gain. So KCL at the emitter. We have a current of VN minus V out divided by R pi flowing in. We have a current of GM times V pi. Well, what's V pi? That VN minus V out. VN is at the positive polarity terminal, V out is at the negative polarity terminal. V pi is VN minus V out. And this is going to be equal to current flowing out of the emitter terminal, which is just V out divided by R naught in parallel with RE. So now I'm going to make the big step here of moving all of my V out terms to the right-hand side of the equal sign. So over here on the left, I have Vn times 1 over R pi plus GM is equal to V out times 1 over R pi plus GM plus 1 over R naught in parallel with RE, or Vn divided by R pi in parallel with 1 over GM is equal to V out divided by R pi in parallel with R naught in parallel with RE in parallel with 1 over GM. And from here, my voltage gain so let's see. Comes out to be, let's see. R pi in parallel with R naught in parallel with RE in parallel with 1 over GM divided by R pi in parallel with 1 over GM. But that actually looks a little wonky to me. I couldn't find my notes for the voltage gain, but I remember it being easy. So I thought I'd do it on the fly here. I just wanted to see if I've made a mistake algebraically. Does anything about the derivation not make sense? So I factored the 1 over R pi, I factored the GM here. That's a conductance plus a conductance, which looks like two resistances in parallel, so that part checks out. Moving all the V outs over, I have the 1 over R pi from this guy, I have the GM from this guy, I have the 1 over R naught in parallel with R from here. So that's just a bunch of conductances added together, which looks like a restricted series. So that all seems fine. Multiply both sides through by this guy, divide both sides through by VN, and you get V out over VN as this guy over this guy. Okay, algebra seems to work out okay. My hesitation here is because typically this is expressed in a form where it's more easy to see that the voltage gain of this particular circuit is going to be something that's just a little less than one. And I think that's probably buried in the algebra of these parallel things over these other parallel things, right? So bear with me for just a second as I play around with this to see if we can't get that to shake out. Okay. So I'm going to do something here that you guys might find annoying, and I'm not 100% sure that it's going to work out, but we'll give it a whirl because we're way ahead in this class anyway. So you can just see me struggle with math for a couple of minutes. So I'm going to treat R naught in parallel with RE as if that's a single resistance. And I'm going to treat R pi in parallel with 1 over GM as if that's a single resistance, right? So I'm going to look at this as R naught in parallel with RE in parallel with R pi in parallel with 1 over GM. And then all of this is divided by R pi in parallel with 1 over GM. So playing around with this, R naught in parallel with RE, I'm going to have R naught in parallel with RE times R pi in parallel with 1 over GM divided by R naught in parallel with RE plus R pi in parallel with 1 over GM. All of this is divided by R pi, sorry, that should have been in parallel with 1 over GM. And, oh, this was way easier than I thought. This guy right here winds up canceling this guy right here, leaving me with R naught in parallel with RE divided by R naught in parallel with RE plus R pi in parallel with 1 over GM. And now it should be very obvious to see that this is going to be a number that's slightly less than 1. So the reason why I know that this was supposed to come out as something that's slightly less than 1 is because the emitter follower amplifier is the transistor amplifier version of a unity gain buffer, effectively. The gain should be almost 1 all the time, right? So recognizing that R pi is typically much larger than 1 over GM, we have this thing, which is fairly large, plus this thing, which is the same thing, and then something small. So that's always going to come out to be a number that's just a smidge less than 1. All right, so there's our voltage gain in a non-traditional and traditional form. Now let's look at our input resistance. Okay, so I'm going to redraw this circuit a little bit. It's actively going to be like this, but I'm going to draw it in the box form like a circuit one style problem. So we're going to have our input resistance in series with this guy. We're going to have this guy between the red and ground. So here's our test voltage. This is our base terminal. Here's R pi. This is V pi. Here's our emitter terminal. Here we have R naught in parallel with RE. and then flowing from ground towards the emitter, we have a current GMV pipe. So before we start tinkering around with this, does anybody have any problem with how this is drawn? Okay. So to make things a little easier, I'm going to perform the source transformation on this practical current source so that I can just have a simple single loop circuit to look at. So that's going to look like this. And I can very easily see now, this is my test current. And so I test is going to be equal to let me write it this way. I'm doing KVL around this loop. V test is going to be equal to I test times R pi plus R naught in parallel with RE plus GM V pi is hopefully very obviously just I test times R pi. Times R naught in parallel with RE. And from this, our input resistance is just R pi plus R naught in parallel with RE plus GM R pi times R naught in parallel with RE. Since GM times R pi is just beta, we have R pi plus R naught in parallel with RE times a factor of 1 plus beta. Yep. So there's our input resistance. Everybody okay with that? Hopefully no real black magic or anything, just literally circuits one level of analysis here. Our output resistance. So let's talk about, or let's look at how I can draw this thing to be less of a pain in the butt to figure out my output. Okay. So I'm going to wind up turning this guy off and applying a test source here, right? So when I turn this guy off, how does R pi look connected to other things? in parallel with R naught and in parallel with R, right? Yep. So V pi is then just going to be the voltage drop across all of those things in parallel. Um, so what we should have is something that looks like this. Here's my test voltage placed between the emitter terminal and ground. Here's R pi in parallel with R naught in parallel with RE. Here is GMV pi. Yes, sir. What do you mean? Well, it's going in parallel with it. So between the emitter node and ground, because the emitter node is my input terminal. Yeah, no, definitely not in series, in parallel. Good question, though. So finding the output resistance here is also going to be pretty darn trivial, because we just need to do ACL up here and then rearrange things effectively, right? So we can very obviously see that V test is just negative V pi. So I could just as easily have this current flowing down as GMV test. And then our test current is I test will be equal to V test over R pi in parallel with R naught in parallel with RE plus GM V test. And from here, our output resistance would just be V test over I test. So that's going to be the reciprocal of 1 over R pi in parallel with R naught in parallel with RE plus G. And I'm going to put this in a different color because I'm not 100% sure on this, but let me just put it like this. Might be R pi in parallel with R naught in parallel with RE in parallel with 1 over GM, which I'm 80% confident it will come out that way. Because a conductance plus a conductance looks like a resistance in parallel, and that's just one resistance. So. All right. So here is the relationships for our common emitter amplifier. So effectively, if we go way back here, we figured out how that part works. what do you think the impact of this resistor RL is going to have? It'll be in parallel with RE. So everywhere that we saw RE, we now just put RE in parallel with RL, and that's fine. So really, the only thing that we have left to worry about is what happens if there's some resistance at the base. So let's get that sorted out and put these in the right order. My wife's texting me means. Okay. So common collector with base resistance would look something like this, right? So here's VCC. So instead of going through all of the transistor relationship type things, since we know how everything to the right of that dashed line works, I could just as easily say that I have I'm going to call this node right here Vx. This is the Rn of the circuit that we just analyzed a moment ago. This is the voltage gain of the circuit that we analyzed just a moment ago. This is the output resistance of the circuit that we analyzed just a moment ago. So our voltage gain for this network could be found by saying that we're going to have V out over Vx times Vx over Vn, and V out over Vx is just the voltage gain of the last network that we looked at, right? So V out over Vx is just R naught in parallel with Re over R naught in parallel with R plus R pi in parallel with 1 over GM by inspection. What's Vx over Vn? Voltage divider. So Rn prime over Rb plus Rn prime. So let me scroll back up here and find that. So R pi plus I was not paying enough attention. R naught in parallel with RE times beta plus 1 over RB plus R pi plus R naught in parallel with RE times beta plus 1. Multiply those two things together, we have our voltage gain of our system. What is our input resistance going to look like? Yeah, RB in series with RN front. Absolutely. What's our output resistance going to look like? R out. All right. No, it is applying a equivalent circuit model that's much easier to use to make the math significantly less terrifying. So the MOSFET version of this circuit, which is commonly called a source follower or a common drain amplifier, is going to have similar relationships and all of that kind of stuff. So if we were trying to calculate our voltage gain, I would actually wind up just using this guy right here. R pi is going to look like infinity, which means, yeah, R pi is going to look like infinity, which means we can just drop it from the numerator and from the denominator. So our voltage gain is literally just going to be Vm times R naught in parallel with will be R F in parallel with 1 over Dm. Nothing remotely hard there. For our input resistance, this is going to be a little bit more difficult, so we might have to take a stab at looking at this thing, because we have R pi, which is infinite, and then we have Vm R pi over here. So let's take a look at what the input resistance of the MOSFET version is going to look like. Okay. So this is our common drain. VDD V out, RS, VN. Small signal model, we would have our input signal applied at our gate. Here's our resistor RS, over which we're taking our output voltage. GM VGS. R naught like so. Very obviously, we can see that R naught is just going to look like it's in parallel with RS. And now let's find what our input resistance happens to be. Okay, so I think it might just be infinity. It has to be infinity because there's no current. Yeah, it's just infinity. Okay, that checks out. That's what the math kind of looked like before earlier. Just wanted to make sure. Okay, just infinity. Doesn't need to be any more difficult than that. All right. Output resistance is going to be literally the exact same. Okay, so we're done with the class. Um, the Friday that we get back from the Mardi Gras break, I'm going to lay a little bit of groundwork for integrated circuit versions of these type of things. And then that's what we'll cover for the remainder of the class. But for all intents and purposes, we're actually done. Like 2 weeks earlier, something back there and saying like that. So, okay. All right. All right, yeah, so unless anybody's got any questions, I'm gonna go hide in my office for half an hour before I go teach another class. Yes. Sorry, what was that? Yes, actually. So you're gonna have one design project that will be effectively just setting up a bias network under a specific constraint. So I might have you design either a MOSFET or a BJT 4-resistor bias network with a target current. So I'm going to tell you what the parameters of the transistor device is, and then you have to figure out what all of the resistors are to meet that design constraint. So there's going to be one that's a MOSFET, one that's a BJT. You will do one of them for your test. You will do the other one with your group. Okay. There's also going to be a design project, and I need to look at this one for sure, because I think I might have been giving it in 336, but because we're ahead, I can just give it to you now, and it'll serve as the bridge for when we talk about frequency domain analysis of these circuits next quarter. And so that is literally just a single circuit where you're just sorting things out, kind of thing. So yes, there will definitely be at least one more design project, possibly two. Expect 2 to 3 more homework assignments. Like I said, one for common emitter / common source amplifiers, one for common base / common gate amplifiers, one for common drain / common, what is left here? Collector. There we go. Yeah. Yeah, Brody. No, so I still have to do that. So I will do that probably this afternoon or tomorrow at the latest. I have the problem that I want you guys to analyze written out. I don't have the design prompts written out. And until I get that done, I can't say, do one of these design prompts for your test. So that's all it's waiting on. Yep.
Earlier on the test, when you're deriving, you turn GM times R pi into 1 plus beta. I just wanted to see how that happens.
So GM times R pi is not 1 plus beta, it's just beta.
Oh.
By definition. So somewhere, not there, I don't think. I think it was before that. I distinctly remember doing it. Right here. Yeah, so I have a beta times R naught in parallel with RE, and I have a 1 times R naught in parallel with RE. So that's why it looks like beta plus 1 times R naught in parallel with RE.
That makes sense. Follow-up question.
Yes.
How is GM R pi?
That's literally the definition. Yep.
Okay. I just want to make sure.
All right, I'm gonna go sit in my office in the dark.